All right, welcome back. So what we're going to do now is talk about something called a DApp. What is a DApp, Kevin?
A distributed application.
Okay, so we've talked about the idea of Ethereum, the fact that you can write code that runs across the blockchain, distributed across the entire network. So what we'll do now is actually walk through some sort of slightly dumbed down code and actually show an implementation. So it's not going to be
dumbed down.
Okay, it's not going to be step by step how to create a DApp, a distributed application, but it's going to walk through the important parts, the idea of having code that runs across all these computers. We're going to show you some code, and we're going to walk through what happens, how code is included in transactions.
So yeah, just the basics.
Yes, but this is not supposed to be, introduction to coding in Solidity or introduction to writing your first distributed application, your first contract, getting it up and running. This is really more about breaking down the basics, how it works. Also, you don't need to know how to code to watch this.
No. So pictured here is a contract, and applications on the Ethereum blockchain are called contracts. And this contract is written in approximately, a little bit simplified, but a language called Solidity. And Solidity is one of the primary programming languages on the blockchain.
Most contracts, a lot of contracts are very, very complicated. For example, you can implement a voting app, which it's still not that bad, but it's a lot more code than this. But this is the simplest possible thing we could think of. All that you do, we have a number that we're keeping track of. It's called stored data. And it's going to start at 0 for everybody. And then once it's up and running on the network, anybody can then say, I want to add 5 to stored data. I want to add 1. I want to add 50. I want to add any number. And if you care about the code, this isn't that important. You can call this thing it's called a function called add. And I don't want to confuse anyone, but you can pass in a new number. So you can say, I want to add in 5. I want to add in 10. I want to add in 20. And it will be added to the current total. So it starts at 0. Kevin says, add 5, and then it goes up to 5. And it will go up to 5 across the entire network. So it's not just on Kevin's copy. The entire network will update. So anyway, it's a really simple idea. But it's sort of the building block for something like a crowdfunding application where people are going to contribute money for my Kickstarter on Ethereum. People will submit $10 and $50 and $1,000, and we're going to total it all up somewhere and keep track of that. But this is just the super dumbed down version with no real money involved.
So you might be wondering how people communicate with this contract. In the same way that people can send a transaction on the Bitcoin blockchain to another address. You can send Bitcoin to an address. You can communicate with contracts with transactions.
So as Kevin mentioned, you can write a contract code. This is our contract, just condensed, and it gets its own address. Just like here, we have a person who has an address, and these are super shortened addresses, but they're in reality much longer. Mm-hmm. But for example, the address 05. That's where we're going to send transactions to hit this contract if we want to increment or add to our variable, our piece of data. Or if I wanted to send money, Ethereum, to this green woman, I could send it to 08. Or here's a different contract we're not going to talk about at 09. So on the network, addresses can belong to a person, which we have a slide on this like a million times in the course. You're probably sick of it. Addresses can be a person or a contract code. So we're going to walk through our idea with accumulate. You can see that fancy
I put a lot of effort into that.
Okay. Yeah. So here's our code again. And remember, at the very beginning, we set this up. We're not talking about how we set it up, how we initialize everything. It's up and running on the network. Everybody's computer, all miners, are running this, and stored data starts at 0. That's the default, as you can see here. We start stored data equals 0.
Yeah, and this little rectangle, stored data, that 0 is stored on every single miner's computer.
Yeah.
There might be some miners might disagree, and they might have randomly set it to another number, but remember, this is about consensus. Most of the network, in this case probably all of the network, has that little piece of memory that is for stored data, and it's a 0 right now. So let's see what happens when this contract starts receiving messages.
So the format of the messages, the only thing people can tell our code to do is to add something. So again, we haven't explained functions. If you don't know what they are, don't worry. Just know that if somebody sends a line of code that says add and then a number, we're going to take that number and add it to stored data across the entire network. So somebody sends basically a transaction to our address for the contract. So this isn't to a person, this is to a contract, our accumulate contract, and the message, the data just says add 0. So that's actually, why did we start with that? It's kind of pointless.
That was pointless. They're playing a joke.
Okay, somebody else sends another transaction.
So they send this transaction, add 1, to number 5, which is where our contract lives in memory, and you'll see that stored data increments by 1.
Yes, and that's on all computers on the network, barring somebody being disconnected or someone disagreeing somehow. But in general, the consensus is that stored data is now 1.
So next one comes in, someone adds 1, and stored data, all the computers on the network, all the miners on the network see the add 1 and increment stored data to 2. Next one comes in, add 2, they increment to 4.
Right.
Next one comes in, they add 3, and they increment to 7.
So we should note that these could be coming from entirely different people. The way our contract is set up, it doesn't matter. You don't have to have permission to add. Anybody can send a transaction. So this could be one person, this another person, or they could all be the same person. It doesn't really matter. In reality, when you write a contract, you usually don't want just anybody to be able to manipulate your data and change things. And this is not a course on writing contracts and on Solidity and the syntax, but if you did take a course, they would show you how to handle that and how to prevent that, how to basically add in authentication. So finally, we add 5. Oh no.
Oh,
last one is
8. 8, surprise.
So our total has been updated to 20, and all computers on the network should have 20.
And we'll talk about why this is useful and why someone might want to do this. They're probably not going to do it with just stored data and one number. But what we're describing here is really the base example of running an application on a blockchain.
Yes. And it's kind of weird, but you send these transactions or these sort of transactions to an address, which is not a person. It's code or it's an application, and it's waiting to hear instructions. It's waiting to basically get a message about what to do next. And usually they're way more complicated, but the idea is the same. Fundamentally, someone, or it could be another contract talking to another contract, is sending code.
So right now this just exists on the blockchain, and it's sort of hard to interface with for the average person. So what a lot of contracts have is they have an interface. They have a front end on the actual, for example, on a web browser.
Okay. So up until this point, everything we've shown you is happening behind the scenes. You basically have to be a miner or you have to understand code in order to really know what's happening at any given point. And the same could be said of pretty much any application or any website that you use, except for the fact that most applications have some sort of interface, something that's pretty or easy to understand for humans that you can look at. So for example, Airbnb's front end, or any website. You go to a website, the data itself is ugly, it's stored in computers, it's hard to look at, but it's displayed in a nice way for humans to understand. So we could do the same thing with any Ethereum contract, which is what we're kind of showing here. We could have a website, and this website just provides a window into our data. So it's not going to allow you to manipulate things. You can't change anything. It's just showing you what's there. Just like when you go to, NewYorkTimes.com, you can see the latest news stories, but you're not making news stories or you're not changing them. You're just viewing them. Same idea here. So we can have a little website, and again, don't worry about the code. But if you look at this, we're sort of in JavaScript.
If you understand it.
We're writing code that says, I want to connect to the Ethereum contract with the address 0x or 05, which is not really what an address looks like in the real world, but it's short and it fits on the slide. And that matches what we see here, although I think we actually added an extra 0.
Pretend there's a 0 on the other side.
So imagine though, what we're doing here is just saying, all right, connect to the contract at this address and let me have access so I can just look at what's going on there. And then we can display it. So we can see it starts at 0. And then if we waited a couple minutes, all these ads happened, all these transactions to our contract happened. If we refresh that web page, it would now display the up-to-date total. So not that useful, but imagine that you're building more complex applications. So we said building a dating site isn't really a great idea in our opinion, but the people who did build a dating site, they need some way for people to look at what's going on. They need an interface. So they have some sort of front end on, I assume, in the browser. Maybe it's an iPhone app or a computer app. I don't know. But there's some interface that is connecting to the blockchain.
And also, just a note, I have no idea what is at https accumulator.com. We don't condone anything that happens on that website. You probably don't want to visit it.
To summarize all of this, if that front end thing lost you, don't worry about that. The focus really is that we write code, whatever language we use. This one is sort of a bastardization of something called Solidity.
Say that.
I think bastardization isn't a bad word, is it?
Swear words.
Okay. It's a watered down version of Solidity, a simplified version. Doesn't matter, but we write code, and this contract has its own special address, 05, people can send transactions or sort of transactions containing instructions, pieces of data to that address. And that's pretty cool. Welcome back. What we're going to do now is take a look at the Ethereum blockchain. So the blockchain explorer that we've been using only works for Bitcoin. So this is a different one. It's called Etherscan, and it allows us to just look at the transactions. So here on the home page, you can see a list of recent transactions. And the first thing, and we can see the block that they're in. So all of these are in the same block, 5541409. Then we can see the from address and the to address. And you can see over here is the value, 1 Ether, 0.995, 0, 1.0, blah, blah, blah. Let's start by just taking a look at one of these transactions, like this one right here, which is from this address to that address for 1 Ether. If we look at it, we can see that, what is there really to see? It was successful, the block that it's in, the from address, the to address, the value, about $669 at the time. We're going to talk about gas in a little bit. And then we can see this field, input data, there was nothing sent.
So 0x is code word for nothing.
So this tells us this is a transaction from one person to another person. Or I guess it doesn't have to be a person who's sending it, but it's a purely financial transaction. There's no data or code involved.
So those are called externally owned accounts. So basically all accounts in Bitcoin are externally owned because people make addresses. In the case of Ether, not all accounts are externally owned. Some of them are contracts.
Now for the cool part, if we look at some of these to addresses, there's a little logo or a symbol here, an icon, that signifies that this is a contract's address. And if we click on one, let's go with, some of them have names, some of them don't, and we can talk about why that happens later. But I'm going to click on this one. It's called CryptoKitties Core. So this CryptoKitties is an application. How would you even explain it, Kevin?
It's sort of like trading cards. It's like Pokemon on the Ethereum blockchain. And we could probably write an entire course on CryptoKitties. But in this case, just think of it as sort of a collectible item. Yeah. And the data in the contract refers to these cats. Felines.
Yeah, okay. So it doesn't really matter. All I wanted to show you is that if you see one of these little icons, this signifies it's a contract. And if we click on one, like the CryptoKitties Core, this is the contracts page that we're viewing. This is not the actual transaction. You can see up top, here's the address of the contract. You can see the creator who created it. But we can also, this is kind of cool, you can view the source code of this. So this is the contract itself. If you look here, contract ownable. And we're not going to look at the code, but this is interesting. You can actually see the code if you wanted to. This is the contract. So just like when in the last video we did the accumulator contract, this is a much more complex one. And the other cool thing, you can see all the transactions that have been sent to this contract. And not only that, but if we look at one of them, like let's just pick this first one, 17 seconds ago, you can see it was sent from this address to the CryptoKitties Core contract address. There was some money involved, but there was also data sent. So if we look at this, breed with auto, this was the function that was called, which this is the whole point of CryptoKitties is that you're basically you have kitties and you breed them together and you try and get rarer kitties, I think is how it works.
Yeah. So matron and sire, you breed a matron and a sire, and out comes a new CryptoKitty.
But that's not really the point of this video. So the cool thing is that you can literally see the code, the message that was sent here. And this is just one going to CryptoKitties. Again, if we go back, we can see, I mean, there's a lot of transactions. 14 seconds ago, another 14 seconds ago. Let's just look.
It's a lot of cat
So here's
breeding.
a different one, create sale auction. So this must be somebody selling.
Someone's auctioning a cat.
Yeah, someone's auctioning a kitty. So here's one. It's still a very small amount, but it's slightly larger. 0.018 Ether was sent. And if we take a look, what was sent is that the message, aside from the money, the $12, was bid on siring auction. So somehow, whatever the game is or
someone
the app.
is bidding on the rights to mate that cat with their cat.
Yeah. So there's money involved, which is why there was Ether contained in the transaction, as well as the input or the data, the message to actually bid that amount. So now what we're looking at is
the CryptoKitties actual website. In the last video, we talked about how you could have a front end, an interface to your contract, and this is the interface to the CryptoKitties application. So those transactions we were looking at, the contract we were looking at just a moment ago, are sort of usable from this interface. So here's the marketplace, and this is where those functions are actually incepted. So we were looking at bids, and they can be created from this interface. And what this means is the average person can interact with the Ethereum blockchain without actually handcrafting those transactions.
Yeah, so if I had an account and I had, however this works, I've actually never used CryptoKitties, but I could go here and yeah, I'd sign in. And then once I signed in, I could submit a bid. And that would generate something like this, a transaction, whatever my bid amount was, bid on Siring auction. Or something like that. I don't know exactly what generates this, but I would assume when you bid on a Siring auction that this is the data that's sent.
Yeah.
So back to just the homepage of all the transactions. Really, the point we want to make here is not to show you CryptoKitties even. That just happened to be one that was a contract that we looked at early on. But it's pretty awesome, in my opinion, that you can actually see how this all works. It's all, I mean, remember, that's the point of the blockchain. It's all out there. It's all public. So we can go and literally see the lines of code that are being sent back and forth. Well, not really back and forth. The lines of code that are being sent one way and then being executed by all the miners. And we can see just regular old transactions. For example, this one right here. Sent from this address to this address, 3.9 Ether. Those are two regular old addresses, no contracts involved. Pretty cool, and hopefully this makes it clearer, even if you don't understand the code. Hopefully it makes it clearer what's actually happening, this idea that you can send code, send instructions in a transaction. Welcome back. Now we're going to talk about something called the Ethereum Virtual Machine, or EVM. So basically, this is the environment where Ethereum is run. On people who are mining Ethereum, who have basically nodes on the network, they don't run Ethereum just on their computer like you would a regular piece of, I don't know, a game or a piece of software, an internet browser. It has to be sandboxed. It has to be kind of hidden away from the rest of the world. And we'll talk about why that is. And the way we do it is using a virtual machine. So first, let's talk about what a virtual machine is.
So some of you might have familiarity with using a virtual machine and may not even know it. A virtual machine is when you actually simulate a computer, a machine, inside of your computer. So right. Pictured here is an ordinary iMac. Silhouette of an iMac with an Apple logo. Now, suppose you need to run some Windows software, as many people often do. You can't just open up a Windows application in Apple or in Mac OS X, but what you can do is you can spin up a piece of software that simulates a PC. So you'll have a window open up that is actually a full booted version of Windows 10 or Windows 7 or XP or whatever your favorite flavor is. And that is actually an entirely virtualized Windows machine.
Right.
And that's useful because you don't actually have to have a physical Windows box, but you can do what a Windows machine can do.
Yeah, although there are some limitations, and you don't want to, like, if you're going to be spending a ton of time on Windows doing some, intense gaming, for example,
no,
you don't want to do this. But it is an option. Like for me, I sometimes do this when I need to record Windows-specific videos for students. Instead of buying a separate Windows machine, I just add some, set up a VM, a Windows install on my Mac, and I can start recording there.
So some terminology real quick. The machine that you're actually running the code on is called the host machine. And then the simulated machine is called the virtual machine. So what does this have to do with Ether? And there are some security implications here. This is why Ethereum runs in a virtual machine. And it's to sandbox it from the rest of a computer. So pictured here is a host machine with the Ethereum virtual machine running in it. And the EVM is a full-fledged but very simple computer that is run on every miner's computer. Now, why do we do that? What's the use of that? We want to prevent the Ethereum virtual machine from reaching out and interacting with any data on the host machine, because there could be viruses, there could be dangerous things, there could be files that we don't want it interacting with.
Or, there could be sensitive files that contains personal information or data that we don't want leaked. And this is on every single miner's computer, however many thousands of them are going. If someone wrote code that just said, send me all the names of the files on the host computer and get an encyclopedia of all the files on all the miners' computers, and that's not good. But the same it could go the other way too. If there was a virus on one of these host computers, we don't want it to interact and screw up the network and get into Ethereum somehow. So we sandbox things, as Kevin's mentioned. And that really just means putting borders, boundaries around sort of the space in your computer. It's sort of a weird foreign concept, but yeah, you can partition part of your computer and basically give it rules.
So the Ethereum virtual machine can't talk to the host machine, but it can talk to the actual Ethereum network. And that's speaking to all the other miners. So it has to speak to other miners, and it has to be able to receive incoming transactions and relay them. So the Ethereum virtual machine has access to a small window of the internet, and that is the Ethereum network. Mm-hmm. It can't just talk to regular websites. It can't go to google.com. It can't check the weather. If you want to include data like that in your application, there are sort of mechanisms, there are ways to do that, but it's not out of the box.
Yeah.
Now, the same goes for the host machine. Your Ethereum virtual machine cannot access files, we said before. And this is to prevent it from, for example, someone writing a contract that says, hey, gather all the files on any miner's computer that are named important.pdf.
Yeah, exactly. So here's a little chart to wrap this up. So a miner's computer can access the internet if the human who owns it is trying to browse, for example. But the section that the EVM is running on, that Ethereum is set up in, can't access the internet. But it can access the Ethereum network. It can communicate with other miners. I mean, that's the whole point. If it couldn't, then we wouldn't have a network. We wouldn't have any sort of distributed way of running code. We wouldn't have the blockchain. So that part's important. Then as far as accessing files on the computer itself,
it can't.
It can't.
Nothing on the host file system, but in exchange, it can access basic CPU functions. It can do things like SHA hashes. It can do multiplication, subtraction, addition.
Exactly.
The basic operations, because it is a simple computer and it needs to be able to access that CPU.
Yeah.
And then last but not least, it cannot access the peripherals of the miner. And a peripheral is referring to things like a camera or a mouse
a
or a printer.
Keyboard. Yeah. It can't access that. It can't, get into the webcam and start taking photos.
No. Unrelated, side by side.
Yeah, these look like they're, comparison and that these are related. They're not. This side, what this is showing is that the EVM, basically, we've said that it can't access the host file system, and that's true, but it still has its own special place to store data because it does need to be able to store information and access it out, but it has its own designated little area that is safe and quarantined from the rest of the computer.
Yeah.
So that if I send, for example, the first contract we showed was that accumulator thing, there needed to be a place to store that value, whatever that value was. It started at 0, we added 5, it went to 5. It has to be stored on each miner's computer, and that's in the EVM, and it's in a special sandboxed area for storage.
And even if that miner turns their computer off and back on, it will still be there when they wake back up.
So that's the EVM, the Ethereum virtual machine, and it's important to understand all of this just so that you can understand how Ethereum is safe. All right, welcome back. So we're going to introduce a topic now that is really central to Ethereum and transactions that we haven't really talked about yet. It's pretty cool. Basically, it's a solution to a problem that can come up when you're running code across a distributed network. So if everything is running code concurrently on the network, all these miners are working on some application at the same time based off of a transaction. If that code has some sort of bug, whether intentional or not, that holds up the network, maybe there's something that's running infinitely, or maybe it's like taking up a huge amount of memory and it's constantly storing new numbers, like every number from 1 to on to infinity in memory. And it's doing that in all however many thousand miners are working at that same moment. That's a huge problem because it's holding up the entire network. No new transactions no code is running if this one thing is hogging all the resources. So Ethereum has a solution to that called gas.
So gas is the internal pricing mechanism for running a transaction on the EVM. And gas exists to limit transactions from overusing the resources of the virtual machine.
Yeah.
Be it intentional or unintentional, you need to have a way that prevents any one user, any one transaction from taking up too much compute or too much memory.
Yeah, basically when you send a transaction and it has some message or some code along with it, you pay some price to get that code to run. And we'll talk more about the details, but first I want to just show you, here's a very small selection of operations and their associated gas cost. So everything that you could do in an application, whether you're adding two numbers or multiplying, for example, has an associated cost. So it's pretty cheap to add two numbers, 3 gas. We'll talk about the actual value, what that means, but 3 units of some gas. To multiply, it's 5.
A little bit more.
To balance, which means to get the balance of an account, to figure out how much ether is in X address. That's 400 gas.
Then if you want to store data, this one at the bottom, S store, is 20,000. And why is that? That's because for these machines, memory is much more valuable than just an individual operation. So if you want to actually store data in the EVM, which you can do, like in our example contract, we stored a number, you have to pay to store that new memory. And this is one of the reasons that the EVM is not a perfect place for every single type of application.
Yeah.
It'd be a terrible place to run a distributed Netflix because it would cost thousands, hundreds of thousands of dollars just to store a video.
Yeah, you're basically paying. I mean, think of all these thousands of computers. You're paying to store whatever piece of data you're storing across all of them at the same time. So it just doesn't make sense for that to be an easy thing to do.
So the gas price is the price in Ethereum per unit of gas, and you don't pay for actual operations. Those prices we showed you on the previous page were not calculated as a number of Ethereum, because the goal is that gas is decoupled from the price of Ethereum. As Ethereum goes up in price, the thinking is that the actual compute should still remain constant or low. If the price of Ethereum balloons 10x, you don't want the price of computation to balloon 10x. So gas prices fluctuate over time.
Yeah. So who sets this gas price?
So the gas price is set by the sender of a transaction. And in the same way that Bitcoin transaction fees are determined by a sender, the gas price is determined by a sender. And with a similar dynamic to Bitcoin, based on the gas price, you're more or less likely to be included in the current block. So if you bid very high, if you're willing to pay a lot for gas, then miners are incentivized to immediately include your transaction. Especially when the network is congested, a higher gas price is more likely to get your transaction into the current block.
Yeah. And if you pay a lower gas price, it's still likely that your transaction will get into a block. It just might have to wait until things have slowed down a lot. There's less traffic on the network. So as we kind of jumped ahead here, we have a slide on this. Bidding a higher gas price makes your transaction more likely to be included in the next block. It incentivizes miners to mine it. One last thing we have to talk about is that you actually don't know exactly how much gas the code that you are starting or triggering may end up incurring, the cost associated with it. Because maybe you think you're doing one thing and something else is actually happening behind the scenes, or there are side effects. There are other transactions that are sent off as a result of your transaction. There could be ripples where all of a sudden there's more code that's running and there's a higher cost, and those could send off ripples. The point is, you don't know ahead of time. So what do?
You set a gas limit. So when you commit an Ether transaction, or before you produce an Ether transaction, what you need to do is you need to set an upper bound on how much gas you're willing to pay. So you might set a gas limit at 200,000, and if your transaction ends up using 250,000 gas, then what will actually happen is the Ethereum virtual machine, the Ethereum network, will reject your transaction. And that means that the operation does not have any effect, but the miners still keep the gas.
So now what we're going to do is take a look and actually show you some examples of gas and the gas price on real transactions. So I'm back on the Ethereum blockchain viewer, or one of them. Let's take a look at, how about this transaction right here? So this was sent from someone to a contract for almost 1 Ether. And if I click on the transaction here, all right, so we can see this is whatever the code was that was the function call. And if we scroll, we don't even need to scroll, but I'll zoom in. You can see that this person set a gas limit of, 110,000 gas. And they set a gas price, which, okay, we haven't talked about units of Ethereum, but this is 0.000, a ton of O for Ether, which the unit is what?
A gigaway. Wei, named after that person, Wei Dai, we mentioned in one of the first videos, is the smallest unit of Ether. I think it's 10 to the negative 18. So it's 1 with 17 zeros in front of it.
Okay. So anyway, this is a unit. So this was the gas price that this person selected. This was the limit. So the maximum amount of fees they would want is this number times this number of Ethereum. But the actual number that was used was right here, 80,000. So the limit was 110,000. The real usage was 80,000. And the total computed price is this many Ether, which is 22 cents.
As of the current exchange rate.
Yes. So you can poke around and take a look at other transactions and see the gas price. But this is not something that you have to, stay up worrying about if you're trying to get into Ether, because most of the time you'll have an estimate of a gas cost for what you're trying to do. The other thing we didn't mention, the gas limit that was set here, whatever was not spent, you are refunded. So you're not just committing whatever, this number of gas times this gas price and just saying goodbye to it. Whatever's unused, you get back. Welcome back. In this video, we're going to demonstrate a real-life Ethereum transaction. And it's actually the first of two videos because remember, Ethereum can be sent to people, to addresses like this, or to addresses that are owned by contracts. So in this video, we're going to do the former. I'm going to have Kevin send me some Ethereum. It's just an address, like peer-to-peer, person-to-person. And rather than doing two different phones, Kevin's phone and my phone, like we did for the wallet apps that we used in the Bitcoin transaction video, I'm going to have him use his phone and send it to a wallet that I'm going to use. It's actually in my browser on my computer. What I'm using is something called MetaMask. It's a very popular Chrome extension that allows you, it basically acts as an Ethereum wallet in your browser. So I've already installed it, but you go to the website, click Get Chrome Extension, and it sets up a wallet for you, and you can access it from this little icon here. So this is my MetaMask account. We set up a new one. He already sent me a little bit of Ethereum. We have a transaction pending. We can ignore this one. We recorded this video a couple times. So I'm gonna just ignore that. I'm gonna ask him to send me some Ethereum from his phone, which has been patiently waiting. What app are you using, Kevin?
I'm gonna use Blockchain.
Okay, Blockchain, which I used for Bitcoin, the Bitcoin video when we did this. So the first thing I need to do is just give him an address. So I'm gonna use a QR code, and he is going to open up his app, click on the to button, or no, there we go. Click on the QR code button, and he scans the address, and then he's going to type in, how much are you sending me?
How much am I going to send you? I'm going to send you 0.075, so we can have some left over. Oh no, 0.75, so we have some left over for the transaction fee.
Okay.
Continue.
All right. Okay, I don't know if you noticed, but this balance just went up. I'm going to view my account on Etherscan, which is like a blockchain viewer, a very commonly used one. You can see now that if we go to the in transactions, this was 49 seconds ago. Kevin sent me 0.0075 Ether. I have it now. Again, my wallet here, I'm using MetaMask, and it's an app that works in the browser. Why would you want a browser-based wallet?
So we use a browser-based wallet in this case for Ethereum because it's a little more useful because we're interacting with applications that have websites.
Yeah.
In the case of Bitcoin, typically it's just person-to-person transactions, so we don't really need anything else beyond just two wallet apps. In the case of Ethereum, what we're doing is we're about to buy CryptoKitties, which is much easier if you actually look at the web interface. So having a browser app or having a browser extension allows you to actually interact with a website using your wallet.
But we didn't do that in this video. We could have done this with any wallet app on the phone. It doesn't have to be in the browser. But next up, we're going to take advantage. I'm going to use this money that Kevin just sent me to buy something with Ethereum. You'll see I'm actually going to send some code in my transaction. So that's coming up next. Welcome back. Just when you thought Ethereum was complicated enough, we have another fun twist for you, something called Ethereum tokens. So tokens are a really powerful feature in Ethereum, but it takes a little bit to explain what they are. We're going to do that now. So get ready. Basically, tokens are a way of implementing your own digital currency on top of Ethereum, which itself is a digital currency. So if you wanted to make a coin, let's say I'm in college and we have a dining hall system, and I'm going to make a currency that we can use, a cryptocurrency, so students can use to buy meal credits or something.
It's going to be called Lunchcoin.
Sure, Lunchcoin. And I want to implement it. I want it to be a cryptocurrency. I want a blockchain. It doesn't really make sense, but let's just say that's what I want. I have a couple of options for doing that.
So the first option is to just build it from scratch. That means write the source code from the beginning.
Yeah, reinvent the wheel, basically.
And that's very difficult to do. It took the person or the people, Satoshi Nakamoto, who did this, were exceptional engineers. And to do this right on the first try is unheard of.
Okay.
The likelihood that you would do it right is virtually next to
none. So that's a
none.
no-go.
So the second way would be just to copy Bitcoin's source code. So you would copy their source code, you would change the word BTC to LUNCH, And then you would just put it on your own miners. You would tell all the students at your school, hey, run mining nodes and then install Lunchcoin software. And then you would have created your own blockchain network.
Okay.
The problem there is you don't have much hash power. So if some evildoer comes in and wants to cripple the network, wants to shut it down, wants to initiate false transactions, they can do it by just eclipsing your miners with a more powerful set of miners, which you can rent.
So basically the problem is you have to recruit your own miners. Bitcoin has thousands and thousands of them across the globe. If you try and recruit your own, it's not very easy to do, and it takes a while to build up a large network.
Yeah, and that's what makes Bitcoin secure. If you were to copy Bitcoin's code but not take all of their miners, you wouldn't have the inherent security of that large of a network, that much hashing power.
Okay, so then the third option.
The third option and the best option, which a lot of people have started to do, is to build a currency on top of Ethereum. Ethereum allows general purpose computation on top of its blockchain. And what you can do with that is you can just say, I'm going to implement my own token in the Ethereum blockchain.
All that you really have to do is say, hey, Ethereum, I'm going to make a token, my own currency. I'm going to call it Lunchcoin. And I want to use your miners. I want to use your network. I want to follow all your rules, but I'm going to add in some special behavior for Lunchcoin. Or I'm just going to have my own logo or whatever it is, but it runs on the existing network. And we can actually see a bunch of examples of this already. Here is a website called Etherscan. There's a couple of these out there to view tokens. And these are all existing tokens. I'm not sure how they're ranked. Is it by
Probably
volume?
market cap. It looks like market cap on the right.
Yeah. So there are a bunch of tokens. We're not really going to go into any right now, but in a little bit, I'm going to show one in particular. Most of these that are listed here actually do something novel, or they have a use. But you could just make a random token called Catcoin, and you could build it on top of Ethereum, and it would all work. And you could do it in a matter of like minutes or hours compared to writing source code for days or weeks.
And then you inherit the security of the Ethereum network. The amount of miners who are applying their hash power to mining Ethereum blocks, that hash power is protecting your contract.
So one example of an actual use of a token that isn't just a nice logo or a different name is something called Golem. We're not really trying to endorse this, by the way, but this is it was already on that webpage that we showed you, and it's easy enough to explain. So Golem is an application that runs on Ethereum that allows people who have idle computer power. So I have this computer on the network, I'm not using it. Well, other people could run code or could do things on this computer. Like the example they give down here somewhere is rendering 3D animations. It takes a lot of time. I could send that and distribute it to someone else's computer and have them do it for me. So that's what Golem is. But they have a token that they use within the app in order to purchase those compute hours, or basically the computing power. So I don't just use pure Ethereum, I use their token internally called, I think it's just called Golem, and I use that to buy computing time.
So this is useful because if you use a token, you don't need an intermediary. You don't need to sign up for a service or a separate website that manages the actual transfer and manages the rental. This is all mediated through the Ethereum blockchain and the contract that was written when this was released.
Yeah, think of it as if you go to a water park or like an arcade or something, maybe a fair. You go to a fair, and if you want to ride the rides, you're not giving dollar bills to the ride attendants. You go and you exchange your dollars for tokens or tickets or something that you hand out, and each ride costs one ticket. And you use those throughout the theme park. So
Ethereum tokens implement something called ERC20. And this is because this is a standard that was created because early on in the Ethereum blockchain, in the existence of Ethereum, people started making these tokens. And in order to standardize them, someone filed something called an ERC. And an ERC stands for an Ethereum request for comment. You might have heard us mention the word BIP in the earlier videos. Those are called Bitcoin improvement proposals. In this case, this is the analog in Ethereum. Now, ERC20 specified a set of methods, specified an interface that any token ought to implement. So if you follow these rules, if you expose a way to get the total supply of the tokens, the balance of an address, to transfer if you are the owner of some tokens, then you adhere to ERC20. And that means that what's useful there is that you can now interact with token wallets. Now, Ethereum wallets will very often have a section inside of them for ERC20 tokens. And that's cool because now if you have some Golem token, if you have some lunch coin, then all of them appear in your wallet as if they were first-class citizens of the Ethereum network. It's important to note that this is not an enforced rule. You can break these rules if you're creating a token, and you can trick wallets into believing them. So it's very important to do your due diligence if you're investing in any of these tokens, very often called ICOs, initial coin offerings, to make sure that you're not part of a scam. Many of these can be scams, but many of them are safe and have demonstrated themselves to be useful.
Welcome back. We're continuing on with Ethereum tokens. We're going to show sort of a walkthrough of how they work, or at least a part of how they work.
Pictured here is a contract, pictured as gears. And in this case, what's happening is watermelon person, pictured on the left, with that, I think that's watermelon green. It's such a perfect color.
Enough of the color.
Watermelon person is going to deploy this contract. It's going to create this ICO, this token, and deploy it to the Ethereum network. And how does she do that?
So again, what that means is this person has written code. They've written, in this case, we're talking about a token, right?
A contract that implements ERC20.
Right. So they've written this contract for, let's just say it's Lunchcoin, and they want to deploy it. They want Lunchcoin to become a token and to get it up and running so people can buy and sell Lunchcoin. So the code is written and it's deployed, what does that mean?
So that just means that watermelon person just writes the code and includes it as the data for a transaction and sends it to a special address. And that special address is 0. If you send a transaction to 0, then the Ethereum network will interpret that transaction as a contract.
Okay. So all that means is that Ethereum in the network basically makes an address, a space for this contract, for our Lunchcoin contract that establishes the token. And we're visualizing that here as this orange little rounded rectangle. We already saw something similar with CryptoKitties, among other addresses we took a look at, where that contract established its own address. It gets this address. So we have people who have addresses and we have contracts that have addresses. So this, whatever this address over here is the Lunchcoin address.
Now we're going to pretend that the initial distribution of Lunchcoin was 1,000 units. And all of them point at the contract creator. So in this case, pretend that watermelon person is the dean of the school. And she created the contract and she initially has all of the tokens.
Okay.
Now, how does she distribute the tokens? Well, pictured here is Tree Man. And Tree Man is a student and needs some lunch tokens. Or maybe he's a teacher because he's about to get 500 of them. Now, how would watermelon person transfer tokens to Tree Man? I'm just going to call them by their color. How would green transfer them to blue? Well, green would then just create a transaction that just says transfer and the address of tree and the amount, 500. Then the watermelon person, the green person, would send it to the contract. In it goes, off to the blockchain, and then once it's hashed in, once it's confirmed, then the contract's internal data will have updated to point at Tree Man. So now the tree address has 500 tokens. And this is really the mechanics of a token. This is just extended out. Now when people are actually using it to buy lunch, they're going to say transfer to the lunch person and give 2 tokens and get a soda. And once it's confirmed, then the soda will be handed over.
And just returning to this slide, this idea, this transfer, so this has to be implemented behind the scenes. You still have to write code to make this sort of thing work and to figure out what the transfer means and all of that. But the key idea is that all that a token is a contract, a special type of contract that has code, that it has its own address like any other contract in Ethereum, and people send transactions to that contract with instructions about what to do with Lunchcoin or Golem coin or whatever. Not Golem coin, just Golem is what it's called, right?
I think Golem, yeah.
But they send instructions. Just like we saw with Simple Turtle, you could send a move right piece of code to the Simple Turtle contract. You can send a transfer Lunchcoin, or you could even have a destroy Lunchcoin if you wanted to, and send that to the lunch coin contract, which is just an address. And then code takes care of that. And Ethereum is backing all of this. All the mining power, the stability of the network is coming from Ethereum. Welcome back. In this video, we're going to talk about a famous hack that took place, a big moment in the history of Ethereum. It was not a hack of or on Ethereum or on the blockchain. It was of a smart contract, but it was a very, very big, well, I shouldn't say big smart contract. It involved a lot of money. This contract was basically dealing with a ton of transactions, and we'll explain why. It was called the DAO, the Decentralized Autonomous Organization. And let's start by just explaining what the DAO was, what its goal was pre-hack. What was it supposed to do?
So the DAO was a little bit like an Ethereum-based Kickstarter. So it was a smart contract that allowed members to bring up proposals, and other members could then vote on whether or not that proposal should be funded.
It's sort of like Shark Tank or like a venture capital
Shark Tank, yeah.
Like a VC firm where, I don't actually know exactly what the projects were, what most of the proposals looked like, but imagine in simple terms, if you had an idea for some sort of Ethereum involved company or project or token, you could propose it and then people would vote and designate funds for you. So the important thing was that there was a pool of money to draw from, just like a VC, a venture capital firm, has a bunch of money, or the sharks on Shark Tank put their money and you can draw from that. Although in this case, unlike Shark Tank, where individual investors are investing, this is the entire organization where you would delegate a certain amount of the pool of Ether. And there was 11,500,000 Ethereum at one point.
At the time, I think Ethereum was about $20 per at its peak before the DAO was actually hacked. So what is that? That's like about $250 million.
Yeah.
So what ended up happening?
So without going into the actual code and how it works, this is very, very simplified. It was a very long contract. But there was this one thing called split. And that's all that we'll say. This was the cause of all the headaches and all the problems. This little thing called split.
And there was a bug in it. And in that bug, if you specifically crafted a message appropriately while a certain proposal was up, you could actually siphon funds out of the DAO into whatever address you wanted. Now, someone discovered this and then sent the message over and over and over and effectively siphoned off a great deal of the DAO's funds.
I think the exact amount was 3.6 million Ethereum.
Yeah, which would have been, what, $70 million?
Well, yeah, and in today's prices, it's way more.
Way more than that. But at the time, it was still a massive heist.
But the crazy thing is that it was all transparent and public that it was happening, because remember that we're just talking about addresses. And so the person or the group who was behind this were sending these messages basically saying, basically taking advantage of this problem in the DAO and siphoning the money off to an address. And this address people could see. And they could see this money sitting there, this 3.6 million Ethereum, and people had to decide, what do we do? How do we fix this? Is there something worth fixing, or is this just totally, maybe a little unethical, or more than a little unethical, but it's legal? Do we change the history of the blockchain to remove this, to undo this? It was really a pivotal moment, and there was a lot of debate over it.
So what they ended up doing is a proposal was brought about to actually return the funds to the investors. And they were going to make a hand modification to the code that would allow investors in the DAO to get their funds back.
And this was very controversial because what they did, the fix, was basically to write some special code, add it in to Ethereum to freeze this one address and freeze the funds in there and prevent them from being spent. And this sort of, even though they didn't really revise the history of the blockchain, this sort of like patchwork, like special, what would you call that?
It's a modification.
A modification that was made is something that a lot of people were uncomfortable with, because yes, it's easy to, I think most people would agree, this person did something unethical, that money should not be spent, but at the same time, where do you draw the line? It becomes this is my least favorite phrase ever in politics, it's a slippery slope. So that's what a lot of people said.
So what did they end up doing? They actually added the switch and they implemented something called a soft fork. So on July 20, 2016, the blockchain actually forked. On the bottom here, this is block 1,920,000, actually created a separate chain because some miners were not interested in installing the actual patch and refused to be part of this rewrite of history. It wasn't really a rewrite, but a modification to the source code of Ethereum in order to refund people.
Yeah, some people are they're strong advocates for complete, laissez-faire attitudes about the blockchain. It is what it is. You've written the code, now leave it and don't meddle in it.
Yeah, and both sides have their merit, but what ultimately happened is most users went with Ethereum, and it was named Ethereum as opposed to a different name. They took the name Ethereum because the majority went with the copy that invalidated all of the theft transactions.
Yep.
And the other chain that persisted, that continued, wherein the transactions were, the DAO had still been funneled off and there had been no remedy for it, is now called Ethereum Classic. It's still a currency, and I believe it's about, what is that? It's $20 compared to the $700 or so that we're looking at for Ethereum now.
Yeah.
So it's 1/35th of the price and approximate market cap of Ethereum's main chain.
So the reason we brought this all up and talked about this hack is, one, to illustrate the fact that there are vulnerabilities when you're talking about smart contracts. You could write bad code because the code just runs as it is in a contract. There was no problem with Ethereum itself here. This was just a really, really large organization, a smart contract that was managing 250 million US dollars at one point. And somebody found a bug in the code and was able to exploit that. That doesn't mean there was a problem with Ethereum itself. The second reason we brought it up is to talk about the repercussions and the split that resulted in Ethereum and Ethereum Classic. And yeah, as we already mentioned, you can buy Ethereum Classic today. It's worth much less, but you can go and see that I think actually those funds have been moved a little bit in Ethereum Classic. Mm-hmm. They're not worth anywhere near what they would be worth in Ethereum, but the person of the group who stole the money from the DAO, I think moved some of them around, cashed a little bit of it out, and you can see it on the blockchain. Anyway, we'll wrap up there.